Okay, guys, so far we've talked conceptually about what the electric field is. In this video, we're going to talk about how to calculate the electric field magnitude and direction with the electric field equation. And we're also going to talk about how we can draw the electric field or represent it on a diagram using lines and vectors. Again, this is kind of review from what you guys did in 183, but again, a little bit higher level. So everything we've done so far has considered the electric force, okay? And if you recall, the strength of that depends on the charge of what we call the test charge, right? The electric force in Coulomb's law depends on two charges, the source charge and the test charge, okay? Defining the electric field, if we calculate something called the electric field, this allows us to describe a quantity, okay, that defines the force that a source charge would experience on any test charge, or really any object in general, okay? And this is the idea that the presence of an electric field does not depend on there being test charges within it. The electric field is there whether anything is experiencing that force or not, okay? So it's nice to have this other quantity called the electric field that just defines the magnitude and strength of that field, okay, without worrying about what the charge of a test charge in it might be, okay? So the electric field, it allows us to define a quantity that indicates the force that a source charge, okay, remember the source charge, that's the thing creating the electric field, would exert on any test charge, okay? Okay, and so if I want to calculate that, basically what I do, the electric field is defined as the electric force, which is given by Coulomb's law, divided by Q, which is the test charge, okay? So again, kind of a lame definition, I think, in physics, but this is the electric force. And this would be a test charge, okay? So if you did have a measurement device that was measuring the electric force experienced by some test charge, in order to get the electric field from that force, you would just divide what you got for the force by the test charge, and you would find what the electric field is. Of course, I could rewrite this equation to do the opposite calculation, and then the electric force would be equal to Q times E, the electric field strength, okay? So electric field is really just a force per unit charge, okay? Because of that, you can imagine that units for the electric field could be, right, newtons over coulombs, that's appropriate units. Later we'll also use, and it's more commonly used, volts over meters. Okay, so that's how we define it. For a collection of point charges, okay, so these are charges where we can assume all of the charge is concentrated at a single point. Our electric field equation would just look like similar to Coulomb's law, but we're going to be missing one of the charges, so we still have this constant out front. Okay, we're going to sum over all of our source charges. Q here, Q sub I, that is the charge of each of our source charges. Our fancy R here, that's the distance from the point that we're trying to measure the electric field to each source charge. Okay, right, and r hat sub I is our unit vector in the direction of that separation vector for each of the source charges. Okay, we talked about when we were thinking about Coulomb's law, you can simplify this part of it here by actually plugging in how you calculate this unit vector. And that gives you a slightly different equation that's a little bit more practical when you're actually making the calculation. Okay, and that's you get the Q sub I, right? That's still the charge of each of your source charges. But now we're dealing with those position vectors. Okay, so I'm going to put a little prime here. R, without the script I and the prime, that's the position vector of the point where you're trying to evaluate the electric field, and our R sub I primes, okay, those are the position vectors of the source field. Okay, so this is going to depend on, this is going to give you the electric field at any position. We can describe a position by a position vector R. Of course, I can replace all of these R's with what they would be in Cartesian coordinates. So that's an X, Y, Z position. And I can also calculate how the electric field depends on X, Y, and Z. Okay, maybe I'll stop the video here and then I'll let the next video talk about electric field lines, just to keep it a little short.